If you've been following the race for end-to-end autonomous driving, you know that simulation is the bottleneck. To train these models reliably, you need high-fidelity, closed-loop environments. That means your scene reconstruction can't just look good from the camera's original path. It needs to hold up when the simulated ego vehicle suddenly swerves, reverses, or takes a completely novel trajectory. That's novel view synthesis, or NVS. But here's the catch. Current 4D Gaussian splatting methods either nail the static geometry and struggle with dynamics, or they model time-varying appearances beautifully, but completely collapse when you change the viewpoint. Until now, nobody could explain exactly why this trade-off exists. A new paper from Tsinghua University, Meituan, and Central University of Finance and Economics just solved it. They proved that this failure isn't a bug in the rendering pipeline. It's a fundamental mathematical identifiability crisis caused by how we collect driving data. And they fixed it with a technique called Orthogonal Projected Gradient. Let's break down why this happens. In autonomous driving, we collect data from a single vehicle moving along a single trajectory. This means your viewing direction isn't independent of time. It's a deterministic function of time. The authors call this singular observation failure. In a perfect multi-view scenario, spatial view-dependency and temporal evolution are orthogonal. You can cleanly separate what an object looks like from different angles versus how it changes over time. But on a 1D driving trajectory, that orthogonality collapses. Mathematically, the spatial basis functions get projected onto the temporal manifold. Because temporal bases like Fourier series are dense in function space, they can approximate any trajectory-projected spatial signal. This creates a subspace inclusion, where the spatial Jacobian becomes a subset of the temporal Jacobian. Now here's where it gets really interesting. The authors use an information geometric diagnostic framework to prove this. They look at the Fisher information matrix, which tells us how sensitive our observations are to changes in the parameters. When the spatial and temporal Jacobians overlap, the FIM becomes rank deficient. The Schur complement for the spatial parameters collapses to 0. According to the Cramér-Rao bound, this means the estimation variance for spatial parameters diverges to infinity. In plain terms, the temporal parameters hijack the spatial ones. The optimizer just lets spatial features drift, because the loss function can't tell the difference between a view-dependent reflection and a time-varying appearance change. When you finally ask the model to render a novel view, those unidentifiable spatial parameters cause catastrophic morphological collapse. So how do you fix a fundamental identifiability failure? You can't just throw more data at it, because the data collection process itself enforces this coupling. The authors propose a hierarchical training strategy called Orthogonal Projected Gradient, or OPG. It's essentially proactive credit assignment. The first stage is straightforward: freeze all temporal parameters and train only the spatial ones. This guarantees that the static geometry and view-dependent appearance are learned cleanly, without interference. Once the spatial manifold is locked in, you move to the second stage. Here's the clever part. You freeze the spatial parameters and optimize the temporal ones, but you don't just use the raw gradients. You project the temporal gradients directly into the null space of the spatial Jacobian. By applying a projector matrix, you mathematically strip away any temporal update that overlaps with spatial view-dependency. This forces the temporal parameters to only capture variations that the spatial model literally cannot explain. The result is a block-diagonal Fisher information matrix. The cross-modal information vanishes, identifiability is restored, and you get stable novel view synthesis without sacrificing temporal modeling. But OPG alone isn't the whole story. By projecting temporal gradients into the spatial null space, you've solved the spatial identifiability problem, but you've created a new vulnerability. The temporal parameters now have infinite variance in the directions orthogonal to the spatial manifold. They're completely unconstrained. If you just train with OPG, the model will overfit to noise in the temporal domain, leading to flickering or unphysical appearance shifts when extrapolating. To fix this, the authors introduce a temporal regularization strategy grounded in a simple physical prior. Object appearance evolves smoothly over time. They add a temporal total variation penalty to the loss function. This penalizes rapid, high-frequency fluctuations in the temporal coefficients, effectively restricting the solution space to physically consistent trajectories. It's a beautiful balance. OPG handles the algebraic decoupling, and the TV penalty handles the statistical regularization. Together, they ensure the reconstructed scene remains physically consistent during closed-loop simulation. When they tested this on the Waymo and OTR dataset, the results were stark. Previous methods like street Gaussians and S3 Gaussian would score incredibly high on standard interpolation metrics, because those metrics only test views along the original data-collecting trajectory. They were essentially overfitting to the trajectory, masking the NVS failure. But when evaluated on true novel view stability, those methods collapsed. The OPG framework matches or exceeds SOTA on interpolation metrics, while completely eliminating the morphological breakdown during view extrapolation. Ablation studies confirm that removing OPG causes specular highlights to bake incorrectly into surfaces, and removing the TV penalty reintroduces temporal instability. Interestingly, they also found that while B-splines act as an implicit regularizer, without OPG, Fourier series become decisively superior, once OPG and TV are applied, thanks to their high-frequency representational capacity. This work is a significant step forward for autonomous driving simulation. It moves us past heuristic fixes and gives us a rigorous, information-theoretic understanding of why 4D reconstruction fails under single trajectory constraints. By decoupling spatial and temporal credit assignment through orthogonal projection and enforcing physical smoothness, we finally get systems that can maintain high-fidelity temporal dynamics without sacrificing novel view stability. For anyone building closed-loop simulators or working on dynamic scene representation, this framework provides a much more robust foundation. If you're interested in the full mathematical derivations, the Fisher information matrix analysis, and the implementation details, I'll leave a link to the paper in the description. Let me know in the comments how you think this approach could scale to non-rigid objects or multi-agent interactions. Thanks for watching, and I'll see you in the next one.